introduction. My name is Andrzej Nowak. I did this work at CERN, the European Organization for Nuclear Research, which is a research lab itself. It's not a university, in collaboration with EPFL, which is itself a university in Switzerland. My co-authors, Ahmad, Yasin, Mendelson, and Willy Zwaenepoel, are from Intel, the Technion Institute, and EPFL, respectively. And I will be talking to you about a short survey that we did on performance counters for workloads that are enterprise-like. So I will explain in a minute what we understand by that. After the previous talk, probably all of you realize what a performance monitoring unit is. It's a unit inside the CPU that sits there and monitors events as they happen. It can monitor cache misses. It can monitor the instructions retired. And the data is very useful if hard to interpret. So I will tell you a little bit about what led us here to this investigation. So a lot of the code that we run looks like this in terms of functions and their contribution to a total profile of instructions retired. So we have a few top hotspots, so to say, and that's already saying too much because they probably consume 5% each or 7% each, and there are maybe 2 or 3 of them. Then we have a few functions that consume 3% or 2%, and then we have a very long tail with a lot of methods that consume very, very little amounts of instructions retired. And this tail can stretch as far as 2,000 methods. Call stacks are very deep, so these are complex C++ applications that basically run on 500,000 cores or something like that. So there is a good incentive to try to optimize that tail because it accounts for a lot of the time spent on a lot of expensive computers. So we look at apps that have these characteristics, and we also know that other big outfits have these characteristics. There was recently a paper from Harvard and Google where they also had similar results. Basically, they were worried that their profiles are very flat, and they were talking about the correspondence of that profile to what they would see inside spec applications or inside Cloud Suite and so on. So we would like to understand basically whether we can use event-based sampling with performance counters and still get some kind of reasonable information about the basic blocks that we're executing. So we would like to have a relatively accurate way of looking at the execution and what kind of basic blocks we're executing during a runtime. So how does event-based sampling work? Let's run quickly through this reminder. We have our program that's being executed. It's got its instruction pointer, and then it causes an event. So let's say this is an instruction retired. So then our performance monitoring counter is going to increment by 1, and it's going to keep doing that for some time. So we can program this counter to overflow once it reaches a predefined amount. So let's say every 2 million instructions, we're going to overflow. Once it overflows, it's going to send a performance monitoring interrupt. And then there's going to be some kind of routine that can do something for us every 2 million instructions. And in this case, we ask it to sample the instruction pointer. So basically, we're going to grab the instruction pointer from the system, and we're going to log it somewhere. We're going to log it for later where we're going to analyze it, and then the workload resumes. Now, the thing is that from all these logged IP samples, we can build an execution profile, so we can see which functions or which address locations we're executing statistically the most instructions. But there are some issues with that because this is not exactly a precise process. And more notably, there are certain places, those marked in gray, where there can be delays or some difficulties with acquiring that sample. So in practice, this means that we have some well-known effects that hinder our progress in terms of collecting instructions retired for all these functions that we're going to run through. And one very typical effect that I can show you, but there are many others, is the event skid. And in this case, we have some timeline. We have instructions that are retiring. And then we notice, okay, at one point there was an overflow because we've reached this magical line of 2 million events or 2 million instructions. So this causes a performance monitoring interrupt. And then there's some kind of a propagation delay. And this delay can vary depending on the manufacturer of the CPU. It can be as short as 8 cycles. It can be much longer. And then you end up in the end with taking a sample of an instruction pointer that was not exactly yours. It might be the next one after the instruction that caused the event, or it might be some other one. So that's called skid, and there are many other events, many other effects that can happen that basically will make it difficult to monitor short basic blocks because accuracy would basically be worse than the size of the basic block. And there's shadowing. There are many other issues there. So the open issues, the motivation for this work are We would like to understand the capabilities of different architectures. These mechanisms are always implemented differently on AMD and Intel, and they vary also significantly between different generations of the CPUs that we were looking at. We would like to understand the characteristics of different methods of sampling. So in the paper, we evaluate about 7 or 8 methods, but they come from 3 major groups, and I will only talk about those in the talk. We would like to understand if we can make software improvements to help the situation. So basically, can we iron out those accuracies somehow by using some kind of smart software-based method? And we would like to understand if the known effects are really a problem in practice, because we know these effects exist, and we know from practice and from other papers that they influence heavily the workloads that we're running. But we would like to understand if kernels or software kernels versus applications would make a difference in that respect. And then in the end, we would like to understand what kind of quantitative improvements we could make. So basically, what is the improvement we could realistically hope for in that respect? And all that to answer the question, at the end of the day, whether event-based profiles can give us accurate or relatively accurate basic block level profiles. So what are the methods we surveyed? One group of methods is the classic one. So there we would basically take the most widely used methods, such as they are implemented in perf, for example, or as they're implemented in major tools. And there we typically have 1 basic block per sample. So basically you take an IP sample and it sits in 1 basic block. Then we would use a so-called precise group of methods, and there we typically try to use the most precise mechanism available on a given architecture. So for example, for AMD, we would use IBS, and then for Intel, we would use PEBS, which is precise event-based sampling, or we would use the precisely distributed variant of PEBS, which comes with the Ivy Bridge architecture. And there we also reduce the known effects, and we get only 1 basic block per sample because we only sample 1 IP. And then we have a facility called last branch records, which is available on a range of CPUs, where we sample untaken branches. And this basically means that we have a buffer in memory that is basically like a stack. And this buffer keeps logging the branches that we went through. And we can filter it to be only taken branches or only non-taken branches and so on and so on. So this kind of sampling approach is available in 2 obscure profilers that you can find today. So we implemented our own variant of it, but that was mostly on the analysis side. So we didn't have to modify collection itself because that's already in perf. We just needed to modify the way it would dump the data, and then we would process it later. So how do last branch records work? This is what a last branch record looks like on Intel. You basically have source and target pairs. And basically it tells you had a source of a branch, you had a target of a branch, and there was a transition between the 2. And then you can say, I only want to monitor taken branches, for example, right? So you would not log into that buffer any branches that you have not taken during the execution of the program. And let's say we have our program. The content is not really important. What is important is to just realize that there are these sources and targets that actually map from the branch record onto the source itself, right? So we have target 14, which maps onto target 14 in the source, and then we have another source 15, which maps onto that source inside the code. And the thing is that in between those, we have 2 branches that were there but were not logged in the buffer because they were not taken, and we would filter only untaken branches. So this mechanism actually enables us, if we take a sample like that, where we have like a mini trace, you would say, of taken branches, then this enables us to take many more samples in a single go. So physically, there's only 1 sample because we copy the contents of that buffer. But in reality, we actually look at many basic blocks during that copying. And this gives us the power to increase the accuracy on one hand because we know exactly what was executed. And on the other hand, we can increase the number of basic blocks that we effectively put in a single sample. So in terms of evaluation of these 3 groups of methods, so the classic one, the precise methods, and let's say those that are based on the last branch record, we used 3 different architectures. We looked at Westmere, we looked at AMD MagnaCourse, and we looked at Intel Ivy Bridge. For all of them, we used perf 3.6.6. That was kind of a sweet spot that we found, which worked very well for all the architectures that we tried. This, as you probably know, perf is a very fluid code base. It changes a lot, it improves a lot, but also there are bugs from time to time, so we needed to work around those. We disabled all the bells and whistles like frequency scaling, NMI watchdogs, and so on and so on. So in this talk, I will focus on Intel Ivy Bridge because this is where the conclusions are most apparent, but if you wish to look at Westmere or AMD results, I invite you to take a look at the paper. So we had four kind of big kernels that we were interested in. One was a very simple kernel, which is basically a loop, and depending on the condition, we execute either a very short latency instruction or a long latency instruction. And this is a typical scenario that is made to trip up the performance monitoring unit, because in that case, due to the effects we were discussing at the beginning, to these known effects, you would actually pile up the samples on one of the instructions, and in this case, it would be the long latency instruction. So you will not get an accurate image of the execution, of the number of instructions that you actually executed inside this sample. So it's already a very good example to try some simple things. Then we had a benchmark called G4box. It's a scientific benchmark, so it's a small kernel again. There is a heavier version of the above, and it executes two functions depending on the conditions. So rather than executing only one instruction, it actually looks at two different functions. Then we had a 10-deep call chain that was embedded inside a loop. So basically, again, you would call 10 deep, and you would return through that, and then you would see what comes out of that and whether you distribute the instructions properly or not. And then we would notice, okay, they're probably not well distributed, and we would look at the reasons why it's not happening. And then we had another scientific code called test40, which is a heavier version of the above kernel. And there, it's an object-oriented physics workload, which basically calls lots of small methods in deep chains, which is something in between a kernel and the mainline production workloads that we have. So we also developed an accuracy metric to deal with to somehow quantify, how good the method is. And in this metric, we would take the number of instructions that we measure using method X inside the basic block. And then we would subtract the reference number of instructions, which we obtained through instrumentation, through PIN. So we treat the number we get from PIN as a holy number. This is the definition. This is the number that we actually believe is the real number of instructions executed. And we would sum all those differences to basically get the total of differences across multiple basic blocks. And we would divide that by the net instruction count of the benchmark. So that's we would say, true instruction count measured by PIN. So you could think of it intuitively as some kind of a fraction that has to do with wrongly attributed instructions. So it's not exactly that fraction, but if you divide it by 2, it would be. And obviously, this metric, we want it to be 0, or we want it to be as close to 0 as possible, because we want the accuracy error to be as low as possible. So if we look at the results for kernels on Ivy Bridge, we would see that the blue bars, so basically the classic methods, are always inferior, and there is a big difference between the precise events and the classic methods. So already by employing the hardware that is already there in most PMUs, by employing the let's say, clever precise events, we get a big improvement. And then if we employ our software method on top of the last branch record, which is also a mechanism available in some modern CPUs, so on Westmere, on Sandy Bridge, Ivy Bridge, and all the recent Intel processors, you can find those, we would get even a further improvement. And sometimes it would be significant, sometimes it would be less significant. And then if we look at apps, we selected the kind of big C++ apps from Spec 2006 CPU, and also much to our, it made us very happy to read in the recent Google paper that they selected some of the same apps to show the kind of long tails that they have in their data center. And these were MCF, Pavray, OmnicPP, and Xalan. And you have similar characteristics in terms of instructions per jump and in terms of instructions per call in those apps as you would have in the long tail apps that we have in our data center. And we also used an app called Full CMS. So this is a Monte Carlo simulation. That's sophisticated physics simulation that has several million lines of code, and it runs about on 300,000 cores, and it runs independently. So each instance and each core is completely independent of another one. But this app consumes a lot of the time we have. And if we look at the raw results, again, we see a very similar picture. We see the classic method is inferior, but the precise method does not produce such significant improvements as in the case of kernels. And then the last branch record method, again, in some cases gives us a big improvement, in some cases gives us a small improvement. So we're already working on a next paper to kind of understand why this is happening, how to improve the situation even further. But in this case, we also see that many different tweaks that we can do, like randomizing the sampling period or something like that, does not bring a significant improvement on apps. So apps behave with sampling slightly differently than kernels and are, let's say, less sensitive to the various methods that we tried. So in terms of recommendations, the full list is in the paper. We think that control over events and distinctions between events matter a lot. So which event you collect is a very important thing. And that's equally, a recommendation for tool developers as it is for regular developers that would work with the events monitoring their code. We advertise to use modern platforms and events. We think that both LBR and precise sampling are already pretty good on many of the architectures that we tested. But we think that minor architectural improvements can be made to make them even better. And then at the end, we believe that LBR-based methods offer enhanced degrees of accuracy. And with a little bit of luck, if we worked on this a little bit more, I think we could input results of those into PGO or some kind of smart compiler optimizations to make them even more efficient. So Ivy Bridge offers us very good features. We found this was the architecture that performed the best. LBR and the precisely distributed event were actually those that gave us the best results. Software improvements can help a lot. So the fact that we've actually wrote an analyzer helped us a lot to get even better results and improve them significantly. We found that known effects in terms of sampling were less pronounced on apps overall, and then you can find the details in our paper. And we found about 5-time improvement on apps and up to 20x on kernels. So again, it shows that apps are less affected by improvements in methods than the kernels. And in the end, our conclusion was that decent basic block level accuracy would be possible with EBS. So we already think that you can improve it a lot by using smarter, more modern methods. And we think that with time, manufacturers are going to introduce some interesting improvements inside their own architectures. So that brings me to the conclusions. We recommend to use precise events. They're basically for free. They're there. And use last branch records whenever they're available for sampling because the gains can be quite good in terms of accuracy. Thank you very much.
So I had at least one question, maybe two. The first one is you said there may be hardware features that can improve the scenario. Do you have an example of one that you might propose, or?
Yeah. So actually, in let's say in the follow-up work that we're looking at, there are certain, you could, for example, take only the top branch of the last branch record instead of taking the whole thing, which architecturally can be a little bit more expensive. You can just take the top branch that you have there, and you can already use that branch to improve the accuracy of the various skid correction mechanisms that exist there. So it's something very cheap. You just copy one register, and that already gives you a good indication of where the sample really was taken.
Hi, I have a small question. How will this work with like JVM based like JIT reduced code, and like do you see any complications with integration with that?
Right. So profiling JVMs is a very, it's a very complex and rich subject. And actually, one of our co-authors, Ahmad, Yasin, produced a paper on that subject. So I'm happy to share it after the talk with you. In general, it is possible. So you can use tools like vTune to profile JVMs, and you get event counts more or less where you would have them inside the JVM. You have many different layers in a Java workload, right? And it's hard to kind of go through all of them and say, okay, this is the line of code where I think the event really occurred. I guess I didn't answer your question directly, but there is hope. Thank you very much.
There are no more questions. Let's thank our speaker one more time.